Okay, so this little lecture is about the phenomenon of interference between waves, means essentially what happens when two waves find themselves in the same place. So here's here's a nice lake. If you found yourself in this place, you'd be all right. Um, we have clearly, you can see waves moving in two directions here, right? One set of waves is moving this direction, another set of waves is moving this direction. And you can see a sort of pattern sets up where you have troughs and ridges. Um, and that's a result of interference and what we call superposition. Okay, what does superposition means? It really just means that waves add to each other, that the amplitudes of the waves, when they happen in the same place or run into each other, um, the amplitude of the two waves sum together. And that can result in what's called constructive or destructive interference, right? So I have two waves here that look very similar but are out of phase with each other. And the result is at any point, if I add this negative x and this positive x, I'm going to get 0. At any point along here, if I add the amplitude of this wave, I'm going to get 0. So we call this destructive interference because the amplitudes act to eliminate the amplitude of the wave. Constructive interference, we see a wave that results that is a sum of the two other waves. So if I add this wave to this wave, which has a very different frequency, I'm just adding this amplitude, whatever this little distance is here, to this distance, and I'm getting that distance. Okay, at a point where I'm at 0 in this wave, I might be a little bit under on this wave, and so I'll be a little bit under there. So we're just adding our amplitudes. This is constructive interference because it creates a new wave and creates a larger amplitude in some places than there were in either of the other waves. So two phrases here, interference and superposition. Interference just means the two waves are running into each other. Superposition means that we're adding those together, adding the amplitudes together. So one type of superposition that results is what's called a standing wave. Standing waves appears not to move, but just to oscillate in place. And a great example of this is a guitar string. So you pluck a guitar string, and it looks like it's just moving back and forth. Really what's happening is you have waves moving up and down that guitar string that are interfering with each other. And the waves that aren't the length of the guitar string tend to get washed out because they hit the end of the string and they lose some of their energy. The ones that survive that process, that initial strike of the guitar string, are the ones that are some division or multiple of the length of that string. So how does that happen? Well, I strike the guitar string, a lot of the frequencies get washed out. And the ones that survive are moving up and down the string. So let's take these two waves. Let's say one wave is moving that to the right and one wave is moving to the left. I add them together here and I get constructive interference on both sides. This one keeps moving this way, and so a moment later I've got completely destructive interference. And then a moment later, they're in phase again, and so I get constructive interference. What does this look like over time? We're moving in time from right to left. It looks like this point is going back and forth, right? It goes here, then it goes to the middle, then it goes to the top, then it goes to the middle, then it goes to the top. So our string looks like it's simply moving back and forth, like a guitar string does, but really what's happening is we have multiple waves moving up and down that string at the same time. So that is a standing wave. A beat is similar in that it's a result of superposition. But this one appears when two waves of similar but not identical frequency interfere with each other. And it's hard to see here, but this wave and this wave have very similar frequencies. but are slightly different, right? This one might be 20 hertz and this one is 19 hertz. Well, what happens is as they sum up, and you could, if you wanted to, you could go down and see, okay, yeah, those are adding there, and here there's mostly destructing each other. You get a wave that looks like this one at the bottom that keeps the general frequency of the two waves, but the amplitude grows and shrinks over a longer period of time. And that's what we call a beat. If you've ever tried to tune a guitar string by playing two strings at once, you listen for it to kind of go between the two strings. If you hear that, that means you're getting a beat interference, and that means the two strings are not the exact same frequency. So you tune it a little bit until you get rid of that beat. We can calculate what the frequency is of the new wave here. So it's the average of the two waves. And the beat frequency we can find is going to be the frequency difference between the two waves. So if I have a 20 hertz wave and a 19 hertz wave, my beat frequency is going to happen once every second. It's going to be 1 hertz. And there's another example there. So let's return to the idea of a standing wave for a second. I said that when we had a guitar, you might strike the string. Some of the frequencies that you are created by that strike are going to kind of wash out because the waves are going to hit the ends of the string in awkward ways, and that's going to kind of kill those waves off. Others are going to exist more happily in that space because they're going to have the nodes of the wave are going to match up with the ends of the guitar string. From this, we can come up with the idea of a fundamental wavelength of a wave. And a fundamental wavelength is equal to 2 times the length of the string. Okay, so my wavelength looks like this, right? This is the length of the string. And so my fundamental wavelength is going to be the largest wavelength I can have that the nodes match up with the two ends of the string. Now, if we think about our equation earlier that our speed of propagation is equal to frequency times wavelength, we can say that our natural frequency is equal to this. Okay, so all we did here was combine this equation with this one. And so that's our fundamental frequency. And frequency is what determines the pitch of our note, of our guitar string. Okay, so when we tighten the guitar string to tune it, what happens? Well, we can't change this fundamental wavelength, but we can change this guy, right? So if you remember, tension was one of the things that controlled speed of propagation. And so tightening that guitar string actually changes the frequency of the played note. Now, the fact that a given string and a given object has a natural frequency, a fundamental frequency, brings up the idea of resonance. A system that has resonant frequencies is going to pick up those frequencies in the environment, right? So if I have my guitar tuned and I hum really loudly a particular note, the guitar string that's tuned to that note will actually pick up those vibrations and amplify them and start to hum itself. And the most famous physics teacher example of this is the Tacoma-Narrows Bridge that, like a guitar string, had 2 endpoints. And the wind blowing over it created frequencies and amplified the natural frequency of the bridge until the bridge essentially destroyed itself. It started to resonate so strongly that it self-destructed. The one we've looked at before is called our fundamental frequency, but we also have what are called overtones, okay, where the nodes still match up with the end, but there are different numbers um, of oscillations within that string. Okay, so this would be called a first overtone here. This would be called a second overtone. And those different frequencies are going to provide different kinds of different notes, of course. With a tube closed on one end, and we can model something like a trumpet there or a clarinet, you have slightly different situations where you don't have a node that works on one end. You have the full amplitude on one end of the tube and a node on the other end of the tube. And that means your fundamental frequencies are slightly different, right? So we're going to have, this ends up being essentially 1/4 of VW over L or 3/4 over VW over L are going to be your different, when N is 1, that's your fundamental frequency. This would be your first overtone. This would be your second overtone, and so forth. Okay, and these overtones are help to explain why when I play the same note on a trumpet and a trombone, they actually sound differently. Or that trumpet and trombone, that's a bad example because those are different registers. But say a trumpet and a clarinet that play the same frequency still sound different. It's because it's not just that fundamental frequency that you're hearing, it's all of the different overtones together.